Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Welcome back to episode 2 about MDMTs. In this presentation, we'll just talk about metallurgy, the ductile to brittle transition, talk about microstructures, talk about stress and geometry and the effects of that, impact testing. So we're going to go and just take a brief look at impact testing. And MDMT stack equipment codes, we're going to wrap it up with that. So let's talk more about ductile brittle transition temperature. This image here is of a Charpy impact test that was performed. And what you can see here is it's indicative of a brittle failure, and it's associated with, a lack of like bending or pulling, and it has a very a surface which is very indicative of cracking, which means it didn't stretch or pull, it just failed in cracking. And of course, materials people have a problem with this kind of crack because this kind of failure can occur very suddenly and result in a catastrophic failure. And here's more of an example of a ductile failure. You can see everything is more elongated. It's much more difficult to fail it. Alloy steels, they have a unique characteristic of a change in properties, in particular the ductility, which is described as the absorbed energy in joules. And as you can see, the material and the upper plateau or the ductile range, which is, for steels is in the normal, like in ambient temperatures, basically, you're going to have the ductility that the designer needs. The part will stretch and pull if it starts to deform. It's not going to suddenly crack and fail like in the lower plateau that you see off to the left, which is shown over here. And so this other zone is called the transition zone. It's sort of a gray area where it's not always certain where that ductile, where it ceases to become ductile and more brittle. But obviously the designers don't want to be in this area. There's a great video here on how a Charpy test is performed, and this is done by a lab, and there's a source there for you if you wish to watch that. And basically that's it. So ASME will allow, if you get into this area, basically ASME and a lot of codes will request that you do additional Charpy testing to prove that the part has enough ductility so that it can be suitable for the service. So it's a very fundamental curve, and it's good to show that. The microstructure is so important when it comes to how tough a steel is, and steel has the microstructure is affected by things like the carbon content, the alloy content, for example, the grain size, and grain size plays a very important role. So a fine grain practice is what you'll see with impact steels, where the grains are controlled with heat treating, and the steel making practice, and even alloying will will affect the grain practice. Coarse grains are never great. They can occur around weld zones because of there's more time for the grains to grow and poor heat treating practices. And this coarse grains can lead to a much higher MDMT for the materials, and that coarse grains can occur in a less processed environment. So, the shape of the grains is another one that's quite important. The structure, the layers inside the structure. Decarburization is an issue where you get carbon leaving certain areas and making the microstructure more vulnerable to cracking. And the effect of the Widmanstätten structure, which is characteristic of during the welding process, that heat affected zone, that intersection between the parent material and the weld material. This is a chart that's quite helpful, and it talks about the different grain sizes, because this is pretty much an optical, like a judgment call. But obviously you can see that very fine grains are more tear resistant, and because of there's a lot, the crack usually follows along the grain, and so large grains have less distance to go for a crack to finish, whereas these have a great deal of distance. And so in steel making, if you want to have impact tested properties, many specs will require that it's made to a fine grain practice. Also, I'll give you an example here. This is also decarburization, example of where carbon has left the area and has changed the properties and is of the material. And depending where the carbon goes, the carbon can make the structure very brittle, and some parts of it overly soft. So then you get a non-uniform grain structure, which is also considered not a preferable situation. There's an example of a Widmanstätten structure, and you can see the undesirable is these long, hard sites along inside the grain, and that makes it more susceptible to cracking. Factors that affect MDMT as external stresses, and they can include internal pressure, weight loads and spans, and secondary stresses, uneven heat distribution, and even occasional loads. And ASME indicates that when one does an MDMT evaluation, that they consider all these variables, and they can be like self-limiting type stresses, whereas if the part flexes, the stresses drop, or non-limiting, like internal pressure doesn't matter. The forces are always there. Those are all factors that one needs to consider. And when there's an analysis, you'll see later that there's something called a stress ratio, and they can be used to take credit for parts that are under low stress as well. Internal stresses can play a big issue on the MDMT as well. One of the most common is residual thermal stresses from welding. ASME can provide a credit for non-code stress, post-weld heat treatment to reduce internal stresses around welds. And accumulation of hydrogen is another one. This can cause embrittlement of the steel and make it more susceptible to brittle fracture when it occurs, when the parts are stressed. And if there's changes in microstructure due to high temperature, and here's an example over here of how creep occurs, and we have other videos on that topic about creep, but you can see how the microstructure, and when you're operating the creep range, it can change, and the grains can get enlarged. You can start to see cracks in the grains, and that will also affect the minimum design metal temperature. So geometry has a great effect on the MDMT as well as the other mechanical properties. But the stress concentrations can affect the MDMT, and it's something to be aware of. So that's just another reason to remove stress concentrations, around holes and notches at the root, and so on. And there's also a phenomenon called the material thickness and the biaxial and triaxial stresses. So thin parts exhibit stresses in 2 planes, whereas thicker parts can exhibit stresses in 3 planes. It's called out of plane shear, and it can act through the wall and increase the stress intensity on flaws at or near the inside surface of a part. So be aware of that, and UCS 66 takes that into account because it's a function also of the thickness of the part, and so basically a very thin part, you'll be able to get more credit for the MDMT as opposed to a thicker part. The other one is material entropy, and that has to do with the properties of a material being the same in all the directions. That's something to be aware of, and good steelmaking practices will so that you have a uniform grain structure in all the directions certainly helps. I know it's in manufacturing. There can be directional directionality with the grains, and it will affect the Young's modulus. And some clients will ask that impacts be done in multiple directions to ensure that the properties are good in all the directions, right? And this is sort of a little chart here taking out of a paper, but you can see how if a part was, if the material was uniform, like its mechanical properties were uniform in all the 4 directions, that would appear more like a cylinder or a circle, right? But you can see that as a material becomes more uniform and like unidirectional, then it'll become more like an ellipse, and it's something to also be aware of. An interesting thing about weld pass size, the smaller the weld size, the more preferential it is on the MDMT. Some codes say, for example, the pressure vessel code, they say do not exceed, half an inch, 12 millimeters. And if you're colder than that, low temperature, then you may be as small as a quarter of an inch, and that has to do with the heat input, I believe, and how it affects the grain structure of the parent material. And some folks call that temper beat. As discussed earlier, toughness testing is a means of assessing the extent to which a material is ductile or brittle, and it's a confirmation to ensure that the properties that are required for a pressure containing component or a load bearing structure meets the requirements. So I'm going to focus a little bit on ASME Section 8 Division 1 UG 84, and this is sort of the standard that you'll see them one of the most common ways of impact testing materials. And everything is, you can see, is very, very tightly specified. And there are other standards that are very similar, and they rely on a pendulum swing to break the specimen, and it's designed in such a way that it takes the friction out of the friction errors associated with breaking the specimen to get the most accurate method. And so that's basically the way that is. Now let's look a little bit more at the advantages and disadvantages of Charpy impact tests. Charpy impact tests are relatively simple procedure. They're one of the most commonly methods around for impact testing. So lots of labs are available. It's very well understood. There's no way that there can be, a mistake. So basically the energy absorbed is the energy required to break the specimen. So it gives you an idea, a percentage of the shear fracture of the material. It gives indication of lateral expansion of the material, and it clearly gives where the transition temperature is, which is really critical, because then you can push your material a little further if you know exactly where that sample, that transition temperature really is. And it determines the toughness in, in different directions. You can do that. You can cut samples that are perpendicular or in different orientations to the way the steel is rolled and made, and also with reference to the weld as well. And so it's a great way to check the directional properties of the materials. But there are disadvantages for the impact tests. Okay. They cannot determine the actual critical size of a defect that would create the failure. Sometimes, it's like there's other tests to assess that, and then there's API 579, the crack assessments as well. There's several models in there, and then that can help give one an idea of doing it. And there's FEA modeling as well, and so on. And they can't determine the crack arrest temperature. These are more of an in-depth study, and what other types of tests would be able to provide that information. So let's look at the codes for new construction. I say new construction because that's for brand new equipment. I just want to make that clear, because we have, PCC2 and 1 and all these other, and we have API 579, which is really for used construction. So for pressure vessels, we have ASME, pressure vessel code section 8, division 1, 2, and 3, right? We have the boiler codes. We have the piping codes, for example, B31.3, one of the most common ones there are, and B31.1, and there's other codes like B31.4, and of course, the pipeline codes. We have atmospheric and low atmospheric tanks, and all these specs have specific requirements for impact testing. B31.4 will lead to later. It actually it doesn't provide anything specific as B31.3 or B31.1. But also going back to the tanks API 620 and 650 have very specific requirements. especially 620, because they're all into the cryogenic type services. So pressure vessels, I want to talk a little bit about that. So pressure vessel codes, I call it the pre-MDMT code revisions, because prior to 1987, there was really no UCS 66 available. I think there was some, like the WRC perhaps documents on that topic. But prior to that, the point is that prior to that, there were no specific rules. And another limitation is UCS applies to new construction only. So the remedy is to follow API 579, and they have a part in there to evaluate the existing vessel if you have an older vessel than 1987, then that's a way of evaluating your component to see where your operating envelope is.